All right, yeah, welcome back again. We want to continue from where we stopped, and this time we want to look at a parametric test. We have discussed so far some assumptions of parametric test, including normal distribution. We have looked at also homogeneity of variance. We also look at outliers. So how to detect and handle outliers in our data. So we have looked at those one. They are very good example on how to check our parametric test assumption before we proceed. Of course, we understand that the parametric test is robust, which implies that you don't need to meet all the assumptions for you to proceed for parametric test. Yes, you can. Some may be violated, not all of them, because parametric test is robust. So if you violate one or two, it doesn't stop you from proceeding to perform your parametric test. But must not violate all. That is dangerous. So that is that for that. So we can check and see if we meet the conditions for parametric test first before you proceed to perform our test. Here, I want to start by single sample t test. When you say single sample t test, we are looking at something like a when you understand a student table test, student table, say we call it student t table. So in those tests, so it's same thing here. It's also used to compare the mean of a sample with a known reference mean. With a known reference mean, you may not have any reference mean at hand, but your reference mean automatically becomes 0. So that's what it means. So if there's not any reference mean, you have your reference mean will be 0. That is the theoretical means will be 0. So in that case, you are trying to compare with 0. You are now saying that the mean of this sample is not equal to 0, or the mean of the sample is equal to 0. But if you have a reference mean, then you can just set your MU to the reference mean, which is any the one that you already have at hand. You want to compare your result with. All right. So we are dealing with the mean of the sample right now. So here we are going to demonstrate this. We're going to curate a data set. We are going to use a sample containing the weight of 20 mice. All right. So let us set a seed first for productivity, and then we're going to say mice. We get a data frame. Let's call a name M1, M2 to M2 to M20. So we are going to create a weight. We're going to round it to 1. Then we create 20. So when we run this line of code now, we have to create it. That's it. Other set has been created. All right. So you can check it. You can glimpse it. Let's glimpse it and see. Mice. Our data set name is mice. Okay. Okay. So we have 20 rows, 2 columns. The name of each mice here is given. Then the weight of each mice is given. Now, since the sample size is not large enough, we have only 20 sample size, which is less than 30. We need to check whether the data follows a normal distribution. So we can just check maybe by using a graphical method. You can show maybe plots, QQ plots to see if you meet it. And you can just pass the weight in and just run. So you can see there's one outlier here, right? Outlier that if you check your I think number 17 now or 16, I think this with outlier. So you can go and check that to do the outlier there. So outlier just one, so that's not a problem. That could be removed. In fact, you can check the outlier by which one is. You can just dollar out. Want to know which one is outlier? Just dollar out and run. Tell you to 24.8 is outlier. So you can do something with it. That you change it, you remove it, whatever you want to do, it's there for you. So I'll give you a lot of examples in the past on that, so you can just tap into it. All right, so let's look at a QQ plot as well. You can see outlier here, see 1, right, out here. You can see, so that's another one here, 2. So the QQ plot is revealing more outlier. So it's just a 1, 2, not too many. They're not too many actually. So we can say that this data is not too far from. Can we plot? Can we see the? Let me see if you can try plot density or density minus dollar weight. Okay, let's try and see just a snapshot of the density plot. All right, so it's not too bad. So you can see the best shape is not too bad here. Okay, not too bad. So, but we cannot conclude that we meet the assumptions for normal distribution. We cannot conclude. Okay, so we have to do a proper statistical test to confirm that we really meet assumptions. So we understand so far we have done several examples in the past on testing, and we have find out that Shapiro is one of the good statistical tests we can use for normality check. So we understand that if the result, which is p-value, is significant, then it means the test fails, right? If it's not significant, I mean talking about if it's less than 0.05, it means significant, which means the test fails. But if it's higher than 0.05, the test pass. So that means we meet the assumption for the normal distribution. So take note of that, okay? Don't forget. So it must not be significant. That's what it means. So I keep repeating that because of many people they do forget. So they just look at the p-value as usual. Okay, so they just see p-value as usual. So they just take it the way it is. So they don't understand the concept behind when we come to Shapiro test, Levin test, Bartlett test, and the rest of those tests. So don't know the difference. So that's why I keep repeating that all the time. All right, so let's run this line and pass our weight here to test if we meet the. So this is a p-value is 0.2 here, which is greater than 0.05, which means we meet the assumption for parametric test. So we don't need to bother to go too further. So you can still test for further if you want, but at least this is enough for simple single t-test is enough. Okay. All right. So let's assume you have a research question. They're saying, is the average weight of the mice differ from 25 gram? That 25 gram happen to be our theoretical uh, gram now, reference me, right? So it happen to be our known reference mean, okay, our known reference mean, which we already have. So if somebody said that I'm aware that 25 gram is the weight of a mouse, okay, that's how somebody give a particular information. So okay, true, really? I'm not. Can we confirm that? Can we test? So we want to confirm if that is true, if that assertion is true or not. So we already have a known mean, or without call it a reference mean or theoretical means. So we want to test that against a mean of new uh, samples that we have gathered together, we have collected. That is called our research question. So we want to say that the average of weight mine is differ from 5 gram. If there is no reference mean, you can say that the average weight of the mice is differ from 0. 0 becomes our reference mean. So that is how you do a simple or single t-test. All right. So let's say we have a null hypothesis created from this research question. The mean weight of the mice is 25 gram. Or alternative hypothesis, the mean weight of the mice is not 25 gram. So if you fall in between any one of them, so we can accept one, and you can reject or we cannot reject. So it depends on the result we get. So let's say average weight of the mice is we want to test now using t-test. You just say t-test. We pass in our weight here. If you attach our mice, okay, as a table, then we don't need to use mice to like I told you before. So just use weight here. Mu is your mean, is your reference mean, that's the mu. So you pass that equal to the 5. If there's no, if there's no mu, by default your reference mean is 0. So just remove this and just close the bracket here. All right, your test will run fine. It is assuming that you have no reference mean and you are comparing with zero, right? That's what it means. So let's run this line of code and see the result. All right, so we have this result. All right, so one sample test data. So our t is this, our degree of freedom is the p-value is highly significant. Alternative hypothesis, true mean is not equal to 25, right? We have 95% confidence interval, which is between this and this. We have 18 lower bound, 20 upper bound. Our estimate is 19.5, so which is different from uh, 25 gram. So this is our mean value we got through the test, which is different from the 25 gram. All right, so which means that we can also use a piping method to do the same thing. Just say my select weight, test passing, so we get the same answer if you run the piping method. So we have the same answer, same result here. So that is piping method. So it is indeed significant, lower than 25. So we could report this as follows: the average weight of the mice was significantly below 25 gram. Using t, our value is this, okay, t 90 degree of freedom. We have it's equal to this. The p value is less than 0.01. You need to write all this, okay, and you say p less than 0.01, right? So if we want to test maybe whether the mean, now this time around, now we can reject non hypothesis and get null. Okay, that says you can reject null, okay, that say the mean weight of the mice is 25 grams. You can reject it now. So in the favor of a alternative hypothesis, which says the mean weight of the mice is not equal to 25 grams. All right, so that is your conclusion in that section. So now we can, if you want to test whether the mean weight of the mice is greater than or less than, that is one tail test. The one we just finished now is two tail, right? Now, what does that mean? Actually, it's very simple. Look at this particular density plot. We have half here down from down here, 20 here. This is half middle, all right? If you draw a line up here, it's half here. So if you are testing for this side, you are testing greater than. You are testing this side less than. It is called one tail. So one tail means one-sided, or this side, either this sided or this side. So, but if you are what we are doing for the both is what we just finished now. It is two tail, all right? So this is just what it means. So we are dealing with both now. That is first thing we just finished now. But if you want to deal with only one side, we call it one-sided, which is one tail, right? One tail this side, or this one is greater than, this one is less than, all right? So when you divide it into these 2 points, all right? So in that case, just say test have the same thing, mu25, that's alternative equal to greater. So if you want to test, that is, we are dealing with this side. Want to deal with this side now, you can say alternative is equal to less. Okay, less. So that is what you do. So it's very simple. So if you run this now, we'll be able to confirm whether it is greater or less. So note that if the data had not normally distributed, it is recommended to use the non-parametric one sample with constant rank test. All right, we're going to be doing that later, but at least let us run parametric first, and we can look at other non-parametric tests. Okay, so this is what you do. So if you run this now, for example, you can see the result. You can do the result. You can see not significant. Why? Because it's not it proves what it says. We are saying that our MU is 25. We are saying that the alternative is greater. Okay, the true mean is greater than 25. So our mean value is 20 is 19. So it's not greater. So it's not positive. It's not significant, right? Right. That is why. So it's not greater. What our mean value is not greater. So if you check to less, let's say we change to less, for example, less, it should be significant now because our mean value will be less truly. So let's see. You can see it's significant now because it's less than what we got is less than 25. All right. So that is how you test using one-sided or one-sided. So it's as simple as that. So that is how you test. So you can pass in other data set and use to test your experiment and see how it goes. So this is just the first section in parametric test that we are going to we will look at more as we continue later. Thank you so much for listening. I will see you in the next class. If you enjoyed the class, you can just subscribe if you are not yet subscribed, and you can comment, you can like. Thank you so much for supporting and for following.